to Eran Palti, yeah, to give us a talk. So if you can share the screen. Yeah, he's coming from Gurion University, and he will talk about convexity of charge operators in CFT and the weak gravity conjecture. So whenever you are ready, Eran, you can start. You have to unmute yourself for this. And also for everyone, like if anyone has any question at any moment, you can just unmute yourself and ask. Okay,
okay. Can you hear me now? Or yes? Okay. Yes. So thank you for the invitation, first of all, to speak. It's a great pleasure. Yes, please interrupt me as much as possible and ask questions during the talk as much as possible. I think that's so. Yeah, if anybody has a question, just interrupt and ask, because I can't see the chat. So yeah. Okay, so this talk is about convexity of charged operators and CFTs and the weak gravity conjecture. It's work that came out just over a month ago with in collaboration with Ofer Aharoni. Okay, so let me begin. So we would like to consider the weak gravity conjecture as proposed in this paper. And it's essentially the statement that should be a particle in a theory with a mass less than its charge. And we will consider this as a statement about particles, so not black holes. So it should be some charge of order 1, basically. So not some very large charge that it's a black hole. So this is the statement we want to consider. And with this statement, we might ask the following questions. What is the appropriate formulation of this in antidecitive space? And this is something that was already being thought about by some people starting with this paper. But we will try to present some other alternative ideas about it. What can the weak gravity conjecture teach us about CFTs? Because if we know how to formulate antidecitive space, then there should be a CFT dual to the weak gravity conjecture. Some statement about the CFT that's dual to the weak gravity conjecture in antidecitive space. So in that sense, if it's true, then maybe it can teach us something about CFTs. And then, of course, we can ask the other question as well. What can CFTs teach us about the weak gravity conjecture? And this is also something that people have thought about. Yeah, I think more in the direction of trying to use CFTs to show or to understand the weak gravity conjecture, a little bit less in the other direction. Yeah, okay, I've given this talk a few times now, so it's the same slides I usually give, so these are a bit basic for this audience, but maybe I'll just go through them quickly to kind of see what kind of motivation there is for the ideas that we want to present. So an old idea is that in quantum gravity, there are no U1 global symmetries. And the simplest argument is that a black hole does not reflect any global symmetry charge in its horizon, at least by the no-hair theorem. And therefore, if you look at a black hole from outside, it could have any global symmetry charge. And therefore, there's an infinite number of microstates that could be associated with a black hole of a fixed mass. And this is in contradiction with the expected finite entropy of black holes. So I think that's probably the simplest argument for the absence of U1 global symmetries. And we can rephrase this argument. We're going to rephrase it a couple of times to try and get to something we can work with a bit more easily. So we can rephrase this as an infinite number of stable black hole remnants, which is really the same kind of statement, but you just, instead of the fixed black hole mass that you hold is going to be around a Planck scale in this case. So basically, there's this idea that you throw in n copies of a charged particle into a black hole with a particle charged with a U1 global symmetry. You let the black hole Hawking radiate away its mass. It cannot emit any global symmetry charge because the horizon shows no sign of the charge. And therefore, you get some remnant, which is charged under the global symmetry. And this remnant is stable. It cannot decay to anything else. It cannot decay, certainly not decay back to the particle which you formed the black hole from. And so it's a statement, it's a remnant, stable remnant. And you can do this with any number of particles, so you get an infinite number of stable remnants. So this is really like the infinite number of microstates, but instead of holding the black hole mass at some large scale, you just let it go down to some fixed low scale. So this is very similar to the previous statement. So this infinite number of stable remnants are closely related to violation of the entropy effect, sign open entropy. Okay. And now you can rephrase this infinite number of stable remnants again. This time it's not really as close to rephrasing, but it's closely tied to it. So instead of taking a lot of particles, forming a big black hole and letting it shed its mass, you can kind of build it up from the bottom instead, this infinite number of stable remnants. You just take the particle charged under global symmetry, you just put next to a copy of itself, and they will attract. And the form a bound state, and the mass to charge ratio of the bound state is going to be less than the mass to charge ratio of the particle, because the charge is going to be the same as twice the charge of the particle, but the mass is going to be a little less. And it's easy to show that if you have an object, it can only decay to something if that something has a smaller mass to charge ratio than it. And therefore, since the bound state has a smaller mass to charge ratio than the particle, it cannot decay back to the particle, and so it's completely stable. If you have more than one particle in the theory, you just have to do this with the one with the smallest mass to charge ratio in the theory. And therefore, this way you form a completely stable bound state. And of course, now you can do this with 3 particles, 4 particles. And if you throw in enough particles, you'll eventually go back up to black holes again and to stable remnants. But you can see this infinite number of stable bound states already from this kind of simple picture.
Can I ask one thing? Yeah. What is the size of these bound states? Is it growing with the number of particles?
Well, eventually it will grow, but yeah, I mean, eventually it will form a black hole, and then of course with a black hole.
But before it forms a black hole, do you know if they all fit in a box of given size, or they're growing and growing and growing?
No, they don't have to. I mean, it's not gonna matter at all for this talk. Actually, what the size of it's just a stable state. But it's an interesting question. I don't really know exactly. I mean, you'd imagine it'd just be like.
Right.
Yeah, like black hole collapse, just how it happens in nature, I guess. I don't know. I mean, yeah, so. No, but of course, the transition through the Planck scale, nobody knows. I mean, yeah.
Right. Yeah. So the reason why I'm asking is because I know you're making different arguments here, but when did you try to relate this, say this, and travel with remnants when you have an infinite number of states, it has to be within a given box, right? Within a certain size, because of course you can have more and more and more states that are getting bigger and bigger and bigger. Like just think of a gas of particles. Like if you take a very big boss of gas, it can have as many states as you want.
Yeah,
I see your point.
Yeah, if you relate it to like the violation of Bekenstein-Hawken entropy, the statement is there's an infinite number of microstates at a fixed mass. Of course, if you allow the mass to be arbitrarily big, then you allow an infinite number of microstates in that sense. Yeah, there's no sharp violation of entropy one can show in this way. So there's always ways. All these things are to do with subtleties that we all know about. I mean, we should mention and important, but we can think of them as motivations at least.
Absolutely.
Yeah, very important subtleties to do with supersymmetry, and I'll come back to that later, because of course we know with supersymmetry you can have an infinite number of stable states. So yeah. Thanks for the question, though. Yeah. Are there any more questions or? Okay, so this is the kind of motivation, and then so now, okay, we don't want a global U1. Let's say we don't like this infinite number of stable states. Then we can gauge the U1, and if we gauge the U1, then the story changes, because now we have not just an attractive force but a repulsive force. And also for the black holes, you have the extremality bound. But if you send the gauge coupling to 0, you essentially recover the same kind of physics. It's just the idea that if you have a U1 gauge symmetry and you send a gauge coupling to 0, it essentially behaves like a global symmetry. So it's not enough to gauge the U1, you should gauge it strongly enough. So what is strongly enough? Well, there's only one other player in this game, gravity. So strongly enough presumably means strongly enough with respect to gravity. So there's a very natural statement you can make. You should gauge it strongly enough so that the repulsive force beats the attractive force. And then you get rid of these stable bound states, they all go away. And similarly, it's exactly the same thing that allows the black holes to decay. So again, you don't have these stable bound states, neither black holes nor the starting level. So this seems to cure all these problems, if they really were problems. which we're going to assume they are. So that's the statement of the weak gravity conjecture. That's the logic of the weak gravity conjecture. But now you can take this logic and you can apply it in more and more situations and see where it takes you. So that's the game we're going to play now. So the first kind of thing we want to do is ask, well, okay, so what happens if there's more forces acting on these particles? Well, if we're talking about long-range forces, there's only one other type of force that can act. That's a scalar force. So scalar forces are attractive between a particle and itself. And so if you add a scalar force to the game, so massive scalar fields that are long-range Coulomb forces, you find an additional attractive interaction. And then you see what we want to do. We want the repulsive force to be not just bigger than gravity, but bigger than gravity plus the scalar. So this is, you follow in this logic, one formulates a different version of the weak gravity conjecture in the presence of scalar fields. And then one can go and test these things in string theory. And this is the plot I like to show by this CERN group, or they were the CERN group, now they've split up. This is a spectrum of particles in F theory construction. And you see here, the y-axis is the charge, and m is the mass, and all these particles have a charge bigger than mass. But there's also a scalar attraction, and the blue line is the sum of all the attractive forces. And then you see these red dots are the particles that are repulsive. And they don't lie exactly on the line, so they're really repulsive particles. And there's a few statements to make about this behavior, which seems to be fairly generic in string compactifications. First of all, we see there's not just one self-repulsive particle, but a lot of them, essentially an infinite number of them. Secondly, you see that the charge of the self-repulsive particle starts with something order 1. Okay, so it doesn't, there's one at charge 1, now there's no one at charge 2, but at charge 3, and so on. But it's something of order 1. It cannot be made parametrically large. And these two properties seem to be universal to any examples that we know of in string theory. So that we're going to use them and assume them. The other important point I wanted to make is that I wrote here in brackets, it's difficult to test in non-supersymmetric theories. And typically I just state that in talks and not really go into it too much. But actually, I think within the expert audience that we have, we're probably aware that this is really a serious issue. I mean, I think it's a very important issue because the weak gravity conjecture is the arguments I just gave you. Essentially, we know it can be violated by BPS states. We can have an infinite number of stable states. And if they're exactly BPS with n equals to supersymmetry, that's not a problem. And we know that the weak gravity conjecture is exactly satisfied or saturated by BPS states. And so the weak gravity conjecture is really a statement about supersymmetry breaking in that sense. So the interesting aspects of the weak gravity conjecture are to do with non-supersymmetric things. And it's very difficult to have scenarios in string theory without supersymmetry. So it's actually very difficult to test what is really the core of the weak gravity conjecture. And this is really a problem because in a smaller program, we want to make conjectures that should be testable, and yet we cannot really test the weak gravity conjecture in really non-supersymmetric settings. And so this is a serious issue that we would really like to address. And one of the things we'll offer in this talk is a way to do that. We reformulate the weak gravity conjecture in such a way that we can test it in truly non-supersymmetric settings.
So what do you mean we cannot test it? We can, of course, test it in non-supersymmetric settings. By that, I mean, when you have a supersymmetric background, you can consider non-supersymmetric states and check it.
Right. So this is why those states are not lying exactly on the line here, the red dots. That's because they're not BPS states. BPS states would exactly lie on the line. Now,
I'm not talking about BPS states. I'm talking about non-BPS states.
These are not BPS states. That's why they're not on the line. Yeah.
Right.
So the only thing we can do about non-supersymmetric things is to look at non-BPS states, but in a supersymmetric setting. And in fact, you can only do it in n equals 2 supersymmetric settings because the only reason these things can lie above the line is because there's scalar fields in the game. If you don't have scalar fields, then essentially BPS state would have a charge equal to mass, and the non-BPS state would have a mass bigger than charge, which violates the conjecture. So the only way that you can really test the conjecture by non-supersymmetric states is when you have massive scalar fields in the theory, and that straight away puts you into n equals 2 settings.
But then you were saying that there's not supersymmetric. Do you mean the bulk, or are you talking about the state itself?
No, the state itself. It's a non-BPS state.
But even in n equal to 2 or higher, you just take non-supersymmetric states and check it. What's the issue?
Exactly. Well, no, the issue is that you have to do this in an n equals 2 setting or higher.
You cannot do you mean you want to have a situation where it's n equals to 1 or less?
Even with n equals 1, you can't do it anymore. But less would be better.
Is that why you said we don't have a setting? I just want to know what you made a strong statement. I just want to know what you're.
Yeah, so my statement is this. We can only test it for non-supersymmetric states in supersymmetric settings, and in fact in extended supersymmetric settings, because we need scalar fields to test it. Otherwise, you cannot even.
But we don't have non-supersymmetric vacuum anyhow, which is stable. So
well, that's the point. So it's very hard to test. We want to test it in truly non-supersymmetric settings, but we can't do that because it's very hard to construct non-supersymmetric vacuum in string theory. So that's an issue. I think it's an important issue because we want things to be testable. And it's one of the things we're going to try and do is reformulate it in such a way that we can test it in truly non-supersymmetric theories. So not just non-supersymmetric states within the supersymmetric theory. Okay, so let's think about this first question then now. What do we do in antidecitive space? So far I've talked about just flat space actually. So if we go back to our logic that we had before, we had this idea of bound states, and we said that what we should have is essentially a self-repulsive particle under all the long-range forces. So why the long-range forces? Well, in flat space, we can take the two particle infinite distance from its copy, and then the only interactions that survive are the long-range Coulomb forces. In ADS space, we can't do that anymore because ADS space essentially acts like a box. And that means it's not actually possible to separate the long-range Coulomb forces from any other kind of interactions with finite range. And so again, we should reformulate we propose that we should reformulate the weak gravity conjecture in NDS space as what we call the positive binding conjecture. Essentially, it's a statement that if you take a weakly coupled gravitational theory with a gauge field, there should be at least one particle in the theory of charge 1, which has a non-negative self-binding energy. Now, in flat space, this statement is the same as saying that the particle is self-repulsive under long-range forces, which is basically the formulation that we previously had. In ADS space, that's no longer true. So here's an example. So one has to now go, according to this conjecture, one has to have a theory. You have to then go and calculate the binding energy of a particle with itself, and then you impose that this should be bigger than 0. And what I want to show now is that this calculation gives you qualitatively and quantitatively different constraints than the previous formulations I gave, both from black hole decay and from self-repulsive particles in terms of long-range forces. So here's an example. We consider 5-dimensional antidecitive space, and we consider this theory here. It has a charge scalar psi, and where we have gravity, antidecitive space, we have a gauge field, we have the charged object as a mass, but now we add these two terms, which are these quartic interaction terms. And we'll see they are very important because when you calculate the binding energy, then these terms contribute to them. And in fact, these are the only terms in the whole action that contribute to the binding energy of the particle at the 2 derivative level. So you could also have a 4 derivative term, but we're not going to include that in our theory. So that shows it's a controllable calculation. We don't have to worry about things like 5 to the 6 and things like that. These are the only terms that contribute. And then you can do the calculation of the binding energy. Luckily, this has already been done in this very nice paper. And one finds 3 contributions. There is the graviton exchange contribution, the gauge field exchange contribution. These are the things we've already been discussing. And then there's these quartic contact term contributions. And this is the result that one finds, that binding energy is the sum of all these 3 things. I've exchanged the mass for this delta. Of course, we will see why that's a natural thing to do, but we can just think of it as a mass, and this is just a calculation. And there is no natural hierarchy actually between the photon and graviton contribution and the quartic terms. So remember, the quartic terms are to do with the fact that they are contact terms, so to do with the fact that the wave function of the particle has a non-trivial overlap with the other one, and that's why there's a non-trivial contribution to binding energy. In flat space, if you take the infinite far apart, there is no overlap of the wave functions, and so the contact terms do not contribute. You can also think of these contact terms as integrating out all the massive mediators of forces in the theory, so just get an effective theory for the particle and the massless fields.
So Eran, here there are no scalar forces yet, right?
Yes, I didn't. It just this is a simpler theory. You could add scalar fields to it, and then you would just get a scalar exchange as well. But we don't need to think about that for now. Yeah, I think it'll be simple. It's a simple calculation to add scalar fields to it. Yeah, and one can check also that in supersymmetric theories. So if this was a supergravity, then the coefficients A and B would be something of order 1. So this is really all 3 terms are basically roughly the same order of magnitude. If you have a BPS state, then you find that this is exactly 0. So BPS states saturate that this whole thing is zero, not that the graviton and photon things are zero, that the quartic term graviton and photon interactions, the sum of this whole thing is zero. So the natural statement you would expect then is to do with the binding energy, because that's what's saturated by BPS states. Are there any questions about this?
Yeah, Eran, can I ask? So there are statements similar to your positive binding conjecture, which you can actually prove if you change charge by spin. Like these go under the name of Nachman's theorem. So it's an old theorem from the 60s, and then people have been working on this recently, like Komarkovsky and Siboedov, and I think recently there's even a proof of some version of it using the Lorentzian inversion formula.
Yeah, so that's okay. So you've jumped to the next step, but of course you can now formulate this as a CFT statement, and then you can prove it in the CFT to do with high spin operators.
Yeah, I just wanted to ask if you.
But it's not related to the spin one, actually. In fact, we'll see that charge behaves very differently to spin.
Okay, thanks.
Yeah. Can I also ask a question?
Yes.
So I was just wondering how this version of the weak gravity conjecture in ADS, how that relates to the extremality bound of black holes in ADS. So, for example, in flat space, you could say that when you impose a weak gravity conjecture, these extremal black holes can decay, and or said differently, in the mild form of the weak gravity conjecture, that shifts the extremality bound a bit. So I was just wondering how that relates to ADS, because then the extremality bound looks a bit different if you look at smaller black holes or larger black holes.
Right. So what we will see is that what this statement really means is that small black holes can decay. At least we will formulate a slightly sharper version of it, and which will hold throughout the whole spectrum. And basically, it will mean that small black holes decay. On the other hand, large black holes will automatically satisfy it. So if you look at the behavior of large black holes, they'll automatically satisfy it. Whilst small black holes, which are like flat space ones, we will argue cannot satisfy it, because you must have some kind of this convex structure. And so, but that's true also in flat space. Okay, maybe I'll formulate it in the CFT, and then we'll talk a little bit about small, large black holes. Can I do that?
Yeah, sure, that's fine.
A bit later. But roughly speaking, small black holes large black holes will automatically satisfy it, and small black holes will not. But I'll talk about that in a bit. So yeah, so this is what positive binding conjecture means, and it's saturated by BPS states, and I think it's a natural formulation according to the logic we just discussed of the weak gravity conjecture in ADS space. It's different to the way it's formulated in the past, so it's a new type of formulation. I should say that. Yeah. So any more questions or? Okay. So there's something very nice about this formulation, which is that it has a very simple dual CFT dual, because the binding energy in the CFT dual is nothing but the anomalous dimension of the operator of the particle. So not the anomalous dimension in the sense of the quantum dimension, take away the classical one, but if we call the operator of the dual CFT phi, that's dual to the particle phi, then the binding energy is nothing but the dimension of the operator phi squared minus twice the dimension of the operator phi. And if you want to make this precise, phi squared is the leading operator in the OPE of phi times phi. So this is kind of clear. Delta is just the energy of the state. So this is the energy of the one particle state phi, and this is the two particle state. That's just the particle in its copy, and you just need the energy of that to be bigger than twice the energy of the particle. That's that is what the binding energy is, and in the CFT, that's what we call this anomalous dimension. So that's very nice because it's a very simple statement in the dual CFT, and we can also write this in an even more general way. Instead of writing it in terms of the dimension of operators in terms of the field, we can write it in terms of the charge of the field under the global U1. So there is a gauge U1 in the bulk, there's a global U1 in the CFT, and now we can assign a charge to the operator that's dual to the field. Its charge will be the same as the charge of the field under the gauge U1. Let's call that Q. That's what it was in the theory I just described. And so the statement is that if you look at the dimension of the operator of charge 2Q minus twice the dimension of the operator charge Q, this must be positive. So that's the CFT formulation of the weak gravity conjecture, or the binding conjecture that we propose. Once you look at the lowest dimension operator, that's the lowest energy state, and when you apply this statement. Now, there's something important here which was confusing to me. many times. When you do the AD-CFT map, multi-particle states map to local operators. So one particle states map, but also two particle states map to a local operator. So in this case, this 2Q state is actually what we might call a two-particle state in a weakly coupled description, but it still maps to a local operator. So we will see that this is important. I mean, it's important to keep that in mind when you're thinking about what this formulation means.
And one question, so naive question, but this anomalous dimension is the same of how much you deviate from the unitarity bound, or it's a different anomalous dimension?
No, it's different. That's what I said. Okay. It's not the unitarity bound is like statement about the dimension versus the classical dimension. So like the quantum dimension must be bigger than 1, essentially, in a weakly coupled theory.
So it's not related in any way.
No.
Okay.
It's exactly what I wrote here. Some people call this anomalous dimension, I think.
But this confuses me. So you have the statement you're distinguishing between two particle states and not two particle states.
No, I'm not distinguishing.
But in the bulk, you could have bound states or non-bound states too. So you're not distinguishing them between them?
No. So this is important.
That sounds a bit strange.
Yes, but in fact, it's really, when you think about it, it'd be the only thing that can ever really make sense, actually, in terms of an exact statement, because there is no sharp distinction between one particle and two particle states in an interacting theory. So in any interacting theory, if you have a two particle state of the same quantum numbers, same charge as a one particle state, then there is no sharp distinction. And if you go to strong coupling, it's very hard to even separate them.
No, for example, when you count the black hole entropy, you don't count the states, multi-particle states as part of the entropy. You count only bound states. So there's very sharp distinction between them.
No, these are still bound states, but it's a multi-particle bound state or a one particle.
Oh no, that was my question. So yes. Of course, that I wasn't asking whether the constituents, how do you count them? That was not my question. No. So the question was that do you consider these as bound states or not?
Yeah. So the bound state story comes in the fact that this is right. Whether it's bigger or smaller than 0.
So they can effectively behave as single particles, even though you call them two particles. Like 3 quarks and a proton, I can call it the proton still, right?
Yeah, there is no, in the CFT, there's no distinction. In the gravity side, what you can distinguish between is something like, let's say the state which has twice the particle, a particle in its copy image, versus some other particle in the theory that has charge 2. So we have, so then you would say there's two types of states of charge 2. One is two particle state, which has the particle in its copy, and one is some other particle that has a charge 2.
But not two particles which repel each other, for example.
Two particles which repel each other is a two particle state.
That's right. We don't want to count those. I'm just trying to say. Or do you want to count them? I just want to know if you're talking about bound states of two particle states or non-bound states of two particle states. Sorry, there's some issue.
Yeah, I think he got frozen. Just wait a bit.
I'll come back soon. I'm sorry, I came back. Is it okay?
Yes. Yeah. Now you're okay. So yes.
I share the screen again. So yes. Yeah, please repeat your question. Sorry.
Yeah, the question was that in the box there's, we have two charge 2, and then there could be 3 different charge 2 states: a single charge 2 state, bound states of 2 charge 1, and unbound states of 2 charge 1. I just want to say that you're distinguishing the latter two or not.
No, not in this formula. Not here. What I wrote here in terms of the operator, of course, it makes no distinction. But you could, on the gravity side, try to distinguish between them. But I don't really see what. The whole point is that we want to make a statement about two particles, whether they bind or repel, whether they're attractive. So
you don't. Okay, because one of them constitutes a black hole, the other one doesn't. Part of the states of a black hole. But again, up to you.
Yeah, none of the, at this level, none of them are black holes. The bound states. If you put them
I know what would be.
Yeah. If you put enough together, they would form a black hole. Yeah. Okay. Yeah. So I want to talk about multi-particle states. Yeah. So it's important. The statement here is about the lowest energy state of a given charge, whether that be one particle or two particle. We don't make a distinction. Okay. It doesn't make a distinction either. Yeah. So this is the dual of the binding conjecture. Are there any questions about this? Because this equation is essentially the core of what I want to say. Okay. So now what we're going to do is we're going to make a wild leap, and we want to go even further. So not only we want to reformulate the weak gravity conjecture in ADS, and we want to talk about this CFT, we want to say that in fact this property that I wrote down here, you see all this property is just a statement about dimension of operators and charges of operators. It doesn't actually make any reference to how many particle states you have, or to forces, or to particles, or even to locality. It's a statement you can make about any CFT. And so we make this wild leap, and we propose that, in fact, since this formulation, we're able to formulate it in such a way that it doesn't seem to demand any weakly curved gravity dual, we propose that the conjecture, in fact, holds for any CFT. Okay, so there's various motivations for this. One is that there is no sharp distinction between what you might call CFTs that are dual to weakly curved gravitational field or to strongly curved gravitational duals. And if there is some property that holds in all CFTs which are weakly curved gravitational duals, it's not that crazy to believe that it should hold for all CFTs altogether. That's one reason. Another one is that the formulation is, the fact that we're able to formulate it in such a general way is giving you a hint that this is a natural statement to make. And the formulation has no problem handling what you would call a CFT dual which is strongly curved. So we can have some idea about this. So we can say, okay, so let's say we made some statement about any quantum theory of gravity. What do we mean by quantum gravity with a strongly curved background? Well, in ADS, we can define it through the CFT dual. And we know what CFTs look like of strongly curved gravity backgrounds, and therefore we can learn what gravity looks like in strongly curved backgrounds. And we know that has things like infinite number of massless high spin fields and things like this. But the conjecture has no problem handling this. It doesn't make any reference to gravitons or to gauge fields and anything like that. And so the fact that you can formulate the statement in such a way that it doesn't care is already a strong hint that perhaps it can hold in such backgrounds. And you should note that a formulation of the weak gravity conjecture, which compares the gauge force and a gravity force, can never really make sense as a statement about any gravitational background, because we know that when you go to strong coupling, that spin 1 and spin 2 fields become part of an infinite tower of massless spin fields. And so there's no particular reason, they're not distinguished in any way. Why would we compare to spin 1 and spin 2? Why not compare to spin 2 and spin 3, or spin 3 and spin 4? It would be very strange to make some statement about some two particular levels in an infinite tower. So the nice thing about the way we formulate it here is it can handle those backgrounds no problem at all.
So let me just make sure I understand here. Suppose you have a CFT, and then you have a U1 current algebra, and your current, you could have some kind of a quotient Z2 of some kind, so that the U1 charge is correlated with some operator. So you cannot have a free U1 by itself. But charge 2 is free. So you can have charge 1, which is always accompanied by an extra operator, but charge 2, which is not accompanied. And I can imagine the dimension of that other operator is so big, so that the dimension of the 2 charge operator is not as big as twice the charge 1 operator. So that would violate your bound. I'm a bit confused. Am I missing something?
So as far as I understand, you're trying to say that you're saying that, sorry, let me understand. You want to say, yeah, you want to take a CFT where the dimension of the charge. Okay. So I'll make the conjecture more precise in a bit. But
yes, this is similar. I should say that this is similar to the counter example we had in the original paper for the stronger statement of the weak gravity, which is
exactly. This is to do with exactly. This is the same kind of discussion that people have had for many years about strong versions of the conjecture and weaker versions.
Strong versions, we had a counter example, which is why we didn't make the strong version, that charge 1 does not satisfy it. Right.
So I will discuss this in a second, actually. Okay. There are strong versions and normal versions of our conjecture. And in fact, I will give an explicit example of what you just said, where the lowest charge operator has twice the dimension of the lowest charge operator is bigger than the dimension.
So the statement you have made is not the conjecture you ultimately will give.
The statement I've made is that this will be true for some order 1 charge. And then there are strong versions of it that I can also make, which will be analogous to this statement. Okay. But I'll make this precise throughout the talk, so we'll come back to that maybe. Yeah. And I will give an explicit example of what you just said, actually. Yeah. So
just as a sanity check, am I right to think that this conjecture is obviously true for a free CFT?
A completely free CFT, yes, it will exactly saturate it. Yeah. But I'll talk about this yeah. So yeah, and the other motivation is that we like to formulate weak architecture as an exact statement. And if you really have an exact statement, then it's hard to think of any other kind of formulation. I mean, if you really have an exact statement, then it's natural to expect that it should hold even moving up to by continuous variation of the increase of the curvature, much like in the kind of way that BPS states hold with continuous variation of the gauge coupling. Or another way to say it, let's say you make some exact statement, so an exact inequality, and then you start adding higher curvature to corrections to your theory. Okay, yeah, R squared, F squared, and so on, and things like this. And then we know that they should modify the theory, but if it's really exact, they can only go in one way, one direction. And so if you make them bigger and bigger, you expect they shouldn't change it. That's again hand wavy, but yeah. So if it's an exact statement, it's probably natural to expect it shouldn't change or be violated as a continuous variation of the curvature as you go to strongly curved backgrounds. So these are the motivations. None of them are particularly, completely convincing, but one uses them, and then we make the conjecture. So this is the statement that called the abelian convex charge conjecture. So consider any CFT with a U1 global symmetry. Denote by delta Q the dimension of the lowest dimension operator of charge Q. Then this must satisfy a convex-like constraint. This is a slightly more general than the example I just gave, but it's essentially motivated by it. That the dimension of the operator of charge N1Q0 plus N2Q0 must be strictly bigger than or equal to the dimension of the charge of the operator N1Q0 plus N2Q0. And this should be true for any positive integers N1 and 2 for some Q0 of order 1. Okay, so what do we mean by order 1? I'll talk about in a second, but are there any questions about this? It's essentially the natural generalization of the argument I just gave, except now if you want to think in terms of bound states, you can just say I take n, n1 copies of the particle in n2, and I don't want these two to add up. Yeah.
So Eran, just to ask, like when you write it like this, it really, if you were to change dimensions by twists, like the dimensions minus angular momentum is exactly this other theorem I was talking about.
Yeah, so convexity is proven for spin, in spin, yes. But in charge it's not. And in fact, the charge will behave very differently to spin.
Yes, yes. So my question was, whether you think that the techniques that people have used to prove it for spins will work for this, or you have no idea? Or
yeah, I don't know because I didn't use those techniques. I gave this talk at CERN a few weeks ago, and Zhibadev said he has some ideas, maybe to do something with this, but I don't know. I do not know how to. It's not my expertise. Yeah. Mm. Okay, are there any more questions or?
Well, there is a comment here. It cannot be as simple a generalization, Miguel, because in that case, presumably there's no minimum, there's no order 1 version of that. You just say the whole statement does not depend on, you don't say L multiple of 5, for example.
Well, there's an analog that you only get this convexity, I think, I might be wrong here, but you only prove it like asymptotically. You don't prove it for. They can have violations of small spins, but also don't quote me on that.
But also the spin is really different because you will show the spin is the convexity goes to 0 for high spin. So essentially it goes to kind of, but we will see that for charge it doesn't. It becomes yeah. So they're really very different in that sense.
But maybe so the convexity is for twist. So that's like dimension minus angular momentum. Maybe for charge it has to be something like dimension minus q to the 3/2 or something like that. Some of the power that. So there's something that goes to 0.
Yeah, there is a universal behavior which I'll show in a second. Yeah. So. So what is Q0? So this is to do with the story that many of us thought about for many years on the gravity side. What is the charge of the particle that the weak architecture is supposed to hold for? And we'll make, first of all, the weak statement, and at the end of the talk, I'll give some strong versions. So from the bound state intuition, we expect it to be the charge of the operator with the smallest dimension to charge ratio in the theory. Those will form the completely stable bound states. That's at least some kind of intuition. And it's also clear that if we define it that way, the conjecture is almost trivial in the sense that if Q0 is the charge of the smallest dimension to charge ratio in an operator in the theory, then obviously the dimension to charge of NQ0 is going to be bigger. and then you just rearrange this and you get basically a version. It's not complete convexity or what is more the statement is actually called superadditivity if you do it precisely, but it's essentially related to convexity. But it's basically kind of convexity. So you also get delta of NQ0 is going to be bigger than NQ0. So there's always going to be some operator in the theory that will satisfy it for sub Q0. Just pick the one which is the smallest dimension to ratio in the theory. The non-trivial statement is Q0 is order 1. So what do we mean by order 1? We mean it's not parametrically large in any parameter of the CFT. Okay, so you take your CFT, take any parameter in that CFT, you can never make Q0 large. So that's the sharp statement, if you like. It's not parametrically large in any parameter of the CFT. And this is really capturing also this positive binding conjecture or the weak gravity conjecture, because remember it's a local operator, but it's due to also multi-particle states. So if your particle could form bound states, then you would just decrease the dimension to charge ratio by just throwing more and more of these particles in. And these multiple states will still be due to local operators. So that means that the lowest dimension to charge ratio operator would be one with very large Q. You could just keep decreasing it, but just by throwing more and more particles in. The fact that they are self-repulsive means that then you can have some order 1Q, which is the lowest dimension to charge ratio operator. Okay, so convexity is capturing the weak gravity conjecture. So if you violate binding energy, you will violate this convexity. But it's not true the other way around. Convexity is a stronger statement than binding energy. And the main difference is to do with the difference between one particle and two particle states and so on. Because we are saying convexity in all the operators, that includes also one particle operators. So if you just have one particle in your theory, there's no difference, because the only charge 2 state you can make is by 2 copies of the particle. But if you have, let's say, also another particle which has charge 2, then convexity holds also for the one particle state. So throughout the whole spectrum. And as we said, that's the only thing that can really make sense if it's a statement is to hold also in strongly coupled theories, because there is no sharp distinction between one particle and two particle states. So this is the only thing that could ever hold true. But it's a stronger statement than binding. That's important to say that. So, okay, so are there any more questions? Because after this, because now I'm just going to move on to tests. Basically, we formulate a more general version, and we'll talk about testing it. Yeah. Okay, so if there's no more questions, so before testing it, we want to formulate a more general version, not just with pure U1. We formulate a kind of non-abelian version, which is really the natural generalization of it. So take a CFT with a continuous global symmetry group G and consider some simple factor inside it, G0. Denote by delta R the dimension of the lowest dimension operator representation R of G. Then there is always some representation R0, that's like Q0, okay, which is non-trivial in G0 and has weights of order 1, okay, so that's like the Q0 of order 1, such that the dimension of this operator, so delta Q of Q, which is the Q symmetric product of this representation. So like Q here is like N in the previous one. So instead of taking N times Q0, now we take the N symmetric product of the representation R0, okay? We look at that operator, and that operator spectrum is convex. So that's the natural generalization to non-abelian symmetries than we have for the U1, basically. So that's what we call the full charge convexity conjecture. And if you take this G0 to be the U1, then it's exactly the same statement we just had.
Eran, I have a couple of questions about the formulation. So you take the symmetrized product here. Is that just for bosons? If you have fermions, you have to take anti-symmetrized, or? No,
it's always symmetrized, but then you have to work a bit harder to construct the things that are symmetrized in representation for the fermions. Yeah.
Okay. I also wanted to know, what do you mean exactly by weights of order 1? Like, suppose that I give you a G which has, like a root lattice which is
not parametrically large in any parameter in the CFT.
Right. What I mean is, a concrete question is, like, if I have a vector with 1,000 components, order 1 is a vector which has 1, 1, 1, 1, 1 in all 1,000 components, or you would say that not too many components have to be different from 0?
Well, the weights should be order 1. So the weights, 1,000 components, the weights are the individual.
So 1, 1, 1, 1, 1 will also count.
Yeah.
Okay.
Yeah. Just to make sure, you're saying that shouldn't depend on any parameters of CFT to be order 1, in particular, like central charge or a function that could go to infinity, and you're saying that even with those, it's not going to scale.
Yeah, exactly. So like large N, it can't go like N, for example, or
that one I can find a counterexample, because you can take, for example, the same example I originally started with. Take many copies of it and take a diagonal U1 in that direction, then that will violate.
Yeah, so multiple U1s is an interesting question.
No, I'm saying take multiple U1s, but look at the AU1 in the diagonal direction. And then the smallest one will have the same.
Yeah, but that's AU. So, okay, so your theory then has multiple U1s, and you want to look at a particular U1 in that theory. So multiple U1s, I'm not going to talk about now, but because in the talk, but we talk about it a little bit in the papers. For now, we can say we're not allowing multiple U1s, because the problem is that once you have two U1s, you actually have an infinite number of U1s, because you can look at any direction you like. And what the weak gravity conjecture is when you have multiple U1s is an open question, really, because then there could be a statement like what you suggest, which is that along any direction of the U1, there must be a weak gravitational particle. But there could also be other versions, which is like, oh, there must be, that's not true along any direction, but it's true again. So the statement we make in the paper is the following, which is a very weak one. We think a stronger one exists. Let's say you have n U1s in your theory. There should exist at least n linearly independent combinations of U1s for which this is true.
Well, the reason I find this a bit surprising, even if there's one U1, this was an example just quickly I made up, but I can make other examples. See, if the central charge is large, you could imagine that that theory have a Zn symmetry for large enough n. So if the larger and larger see, the larger and larger discrete symmetry you can have. And then you can glue that U1 with that Zn action to push that charge all the way up to n. So I could easily imagine that the charge that you will get lower one will scale with the central charge in some way. So I find it's hard to believe that that would be decoupled from.
Well, I don't know which CFT you mean. So perhaps
take for example, take any theory which has some symmetries. There's no bound with the. If you take a larger and larger central charges, there's no reason it cannot have bigger and bigger symmetries. For example, you can have a lattice modeled by symmetries to get rid of U1s, but you will still have discrete Zn symmetries, let's say.
So you mean like adding more and more particles to the theory? You want like, or how you get into the large central charge? Like,
for example, I'm just starting with an easy example. Take like an Eran lattice. Take the toroidal compactification, large dimensions. You can mod that by enough symmetries to get rid of U1s. So there's no U1 in this story. But still, you can have or you can have keep one of the U1s or whatever. But you can somehow connect one of the U1s to some discrete action inside this overflow in such a way that the dimension of the operator non-trivial charge will be connected to the dimension of the operators that you're getting from the CFT side. It's hard for me to believe that you can completely decouple it. That's what I'm saying.
Okay, well, I don't think what this seems. I'll tell you why I think that this cannot be an issue, because the general theorems about how large charge spectrum looks like in CFTs, at least for symmetry. Okay, maybe we'll have to discuss those examples in more detail.
Large for the fixed C you're talking about. That's precisely the point. The theorem you're quoting, which says that if C is fixed, take Q to be large enough, then blah. That has
exactly. Yeah,
I'm talking about you're trying to say Q order 1 regardless of what C is.
Yeah, exactly. That's the whole point.
That's what I have a problem with.
Yeah, then I'll have to think about the examples. Okay. We can discuss those examples a bit later. But yeah, let me carry on. So let's talk about tests of the conjecture. So like I say, if you take a theory then that is sufficiently generic CFT. So now we're just going to talk about CFTs. We're not going to talk about gravitational theories. So we see if this is really true in all CFTs. Could be, if it has a chance to be true in all CFTs. So then you find that the large charge spectrum is convex. So we know that for large enough charge, the spectrum it has some positive coefficient, and the dimension goes like q to d over d minus 1, which is bigger than 1. That essentially ensures convexity. So that means that if you take a sufficiently generic CFT and you go to sufficiently large charge, then you will always satisfy this convexity behavior. And going back to the question about black holes and ADS are essentially the regime where you enter into this scaling. So that's why I said that black holes will satisfy the conjecture automatically, large black holes. Whilst of course small black holes have a linear behavior, which is marginally convex, but it will not satisfy, because if the spectrum is convex and then you reach a linear regime in the middle, then that spectrum will not satisfy convexity. But that's okay, because the weak gravity conjecture tells you that the lowest energy state of a charge Q in your theory is not a black hole of charge Q. it's a collection of weak gravity conjecture particles, essentially infinite distance apart. That is essentially the statement of weak gravity conjecture is precisely that the lowest energy state is not the black hole. So that's perfectly fine because we're just talking about the lowest energy states. So that's the relation to black hole. I don't know. Yeah. So what we know is that for sufficiently generic CFT, sufficiently large Q is okay. And what does large Q mean? It means large relative to any parameter in the theory. So that's what I just discussed also. Come on. So that means that if you have a strongly coupled theory, which has no large parameters at all, so all parameters are order 1, then the conjecture will be satisfied if it's sufficiently generic. So for sufficiently generic, completely strongly coupled CFTs, the conjecture should be true. So that's a good start. If you have supersymmetric theories, then they are not generic. And then you have, or if you have a free scalar theory, you find that the spectrum is marginally convex, so it's linear. And in that sense, it will satisfy convexity, but be marginally convex. That's okay. That's still okay. So supersymmetric theories, if you look at BPS states or free scalar theories, will satisfy this. Of course, if you take a supersymmetric theory, you take a BPS state, and then you consider the higher operators being non-BPS, then you will still have convexity because of the BPS bound. So when you increase the charge, you will have to increase the mass more than the charge. So this will still be convex. In 2D CFTs, one can make an even stronger statement. This is a bit of CFT magic. I don't really know how to get to this, but often worked it out. So in 2D CFTs, if you have a U1 and you have a left and right U1, left moving, right moving U1s, and the spectrum always looks like this. The dimension of the operator is essentially AQ squared, where it's positive, so it's always convex, plus a contribution from some operator in the gauge CFT where you've gauged the U1. Call this the closest CFT. And if these things decouple from each other, then you can always take the unit operator here, and therefore it's exactly AQ squared, and that's always convex. The statement is, as far as I understand, is that nearly always for some Q of order 1, you can take this to be the unit operator, and then the spectrum is convex. But they don't generally decouple, and so there's no proof that you can always take this operator to be something which has charge, which is independent of charge. Some over the 1, so that's why there's no proof for 2D CFTs, but it's looking, pretty reasonable because we always have this convexity bit, so it looks pretty promising for 2D CFTs. In free fermionic theories, I've talked about free scalar theories. In free fermionic theories, the spectrum is not even marginally convex. So if you take Q0 to be equal to the number of components of the fermion, at least. And that's because if Q0 is the number of components of the fermions, if you start to want to increase the charge, you have to put more and more fermions in, but there's Pauli's exclusion principle, which tells you can only put one Grassmannian field in the operator one time. So if you want to put more and more fermions in to increase the charge, what you have to do is put in derivatives into the operator. And if you put in derivatives, then you increase the mass, but you keep the charge the same. So you make the spectrum more and more convex. Okay, so here's an example. If you look at the free fermionic theory in 3 dimensions, the spectrum looks like this, and you see that it's not even marginally convex. 1 and 2 is marginally convex because that's the number of components of the fermion. But if you look at the dimension of charge 2 plus dimension of charge 3, it's not even marginal with respect to the dimension of charge 5. So that tells you that if you have a fermionic theory, and then you do any kind of small perturbation to that theory. So that means if you have any kind of small parameter in your theory that you want to try and compete with Q0 with, then you will maintain convexity because you're just going to be doing a perturbative expansion about a theory that's not even marginally convex. So it will always, so any fermionic theory which is perturbative in any parameter will always have a convex spectrum. So that's also good. The only way out of it is to have a large number of fermions. So the only parameter that can make Q0 large is the number of fermions in the theory, because then you could make operators of a very large charge where you don't have to insert derivatives. So an example of this would be a gauge theory, let's say, and you take the gauge group very, very large. Then you could have a very large number of fermions. So, but any theory with a small number of fermions and which is perturbative, so it has some perturbative parameter, will be convex. If it is not perturbative, it has no small parameter, then it'd be convex by the large charge behavior we just said. So in that sense, the only thing that can test for fermionic theories is large number of fermions. So now we want to test this in explicit theories. And in explicit theories, we have some weak coupling behavior because that's the only way we can calculate anything. So we can assign operators instead of just charges to some fields. Essentially, we're testing something like field to the power of n1 plus n2 minus a dimension field to the n1, field to the n2. And we require this to be positive. So let's look at some theory. So as I said, we know many non-supersymmetric CFTs, but not many. I will essentially go through almost all the examples we know that are controlled. And so this is really non-supersymmetric test. So now we can't get any more marginal convexity apart from the explicit theory. We really get an answer, yes or no. The conjecture is satisfied or not satisfied. So this is nice in that sense. So the simplest theory you could consider is the U1 model in 4 minus epsilon dimensions, so the Wilson-Fisher fixed point. So this is the theory. It's a quartic U1 model, and it has a U1 symmetry, and this is the fixed point of the gauge coupling. This is not a rigorous test because we actually insist on unitary theories for this conjecture to hold, but the interaction with the unitarity is actually something that still needs to be developed and explored. So I think it's perfectly fine to study these in that sense. And one calculates this gamma, which is this convexity parameter that has to be positive, and you find that it's indeed positive for any charge n1 and 2, where n is the power of the field. So actually, interestingly, these calculations were only done recently, so we could read off these results, but they were not even known a few years ago. And there is something else that's nice about this theory. This is a perturbative calculation, so it's true only if n epsilon is small. Okay, so if you take a large enough charge, if n was much bigger than epsilon, then you go into the large charge regime, and then it's true by the large charge behavior, it's convex. If it's intermediate, then it's kind of strongly coupled regime, but you can also show using semi-classical method that the spectrum remains convex all the way. So for any n, even through the strong coupling behavior. So that's quite nice, I think. And that's the simplest kind of theory you can consider. So here's another theory. You consider similarly the ON quartic model in 4 minus epsilon dimension. That's a CFT we can do calculation, and one finds again that it's positive. You can consider the U1 and ON sextic models in 3 minus epsilon dimensions. One can do calculations there, and you find that they are positive. So those are like basically the only things we can calculate with perturbatively, and those kind of theories. The other kind of way you can do things is using large n. And this is nicer because now you can look at unitary theories. So you can look at the ON quartic model in 3 dimensions. That's a unitary CFT, and you can calculate using large n. You find that the quadratic coefficient is positive coefficient. That means that the spectrum is convex. So the conjecture is satisfied. Now, interestingly, you can look at the ON model in 5 dimensions, and you find that here the sign is negative, so the conjecture is violated. And similarly, you can look at the cubic model in 6 minus epsilon dimensions, and these are actually supposed to be related, like UV-IR duality between them. You find again that this is negative. So these theories violate the conjecture, but these theories are also known to be non-unitary, and in fact, they have no vacuum. So that's actually quite interesting. It's a non-trivial test of the conjecture in that sense. So we have examples where you violate it, but this is related to non-unitarity and the non-existence of the vacuum. You can kind of see the direct relation between unitarity and the vacuum just by looking at the U1 model. Since the convexity goes like epsilon, which is just goes like lambda, if I switch lambda to minus lambda, then I violate convexity, but then I also get a runaway behavior. So then I lose my vacuum. So you will see this over and over again, that convexity is related to the existence of a vacuum into unitarity. Any questions so far? Okay. So, you can also look at UM times UN quartic model in 4 minus epsilon dimension, and this is recently calculated, and you find that it's also satisfied. Actually, if you take M and N sufficiently big, you make this theory non-unitary, and then the dimensions become complex. So the conjecture is not supposed to always say nothing about non-unitary theories, but it's interesting that when you do that, you find that the real part of the dimension is still convex. So I don't know what that means, but yeah. So another qualitatively different, so far we've done 2 qualitatively different things, yet another qualitatively different approach is to look at gauge theories. So we can look at Banks-Sachs fixed points of gauge theories, and then we can do a perturbative calculation of the anomalous dimension. So we consider SUNC gauge theory with NF massless fermion and NS massless scalars. And the NS massless scalars have an SUNS global symmetry, and so we're going to look at operators that are charged under them. So because we have scalars, we have to look at a fixed point of this theory. We have to look not just fixed point of gauge coupling, but fixed point of these marginal quartic operators. So we let the coefficients be H tilde and F tilde, and there is indeed such a fixed point. So this is like a Banks-Sachs fixed point with fixed point for these things. So that's a CFT. in 4 dimensions. And we have operators that are charged under the SUNS global symmetry of the scalars. These are these meson kind of operators. Phi star phi, not phi dagger phi, that would be a singlet under the global symmetry group. Here we want to take 2 different global symmetry indices, so it will be transformed essentially as an adjoint, and this would be some nth power of the adjoint representation. And so what we did was actually, so now this has not actually been done, this calculation. So we did it in 1 loop. We calculated the difference in the enormous dimension between the 2 meson operator and the 1 meson one. So that's what we want to test. And one finds that it goes like a positive number times the sum of these quartic coefficients. And then you can show that these quartic coefficients must always be positive. And so the spectrum is convex. And again, we find the same behavior. They have to be positive because if they were not, you would get a runaway behavior. So there'll be no vacuum to the theory. So again, we find a precise match in the parameter space of the CFTs between convexity and vacuum stability. So that's a third qualitatively different check we find on the conjecture that holds. Another more qualitatively different calculation you can do is the following. You can consider 3-dimensional UNC gauge theory with NF fermions, and this flows to a CFT in the infrared. And this CFT has the global symmetry U1 topological. That's the U1 symmetry whose current is dual to the field strength of the gauge field, a la Polyakov. And the operators charged under this U1 topological are the monopole operators. And it turns out that at large NF, you can calculate their dimensions using semi-classical methods. And this is done in these papers. And you find this leading order behavior at F. This is the dimension, this is the charge. And you can check that the spectrum is convex. So if you take 1 plus 2, it's less than 3, and so on and so on. So again, this is completely qualitatively different to all the tests we've done so far, and still we find convexity in the spectrum. You can do similar computations now in 3 dimensions, but not with fermions, but with scalars. And with scalars, you have 2 options. You can have a quartic term or no quartic term. If you have the quartic term, this is what's called the CPN model. If you don't have a quartic term, it's what's called the tricritical model. And one finds that, again, the spectrum is convex. You can also add a sort of Grosvenor quartic couplings for the fermions, which is a deformation of the previous one. And one, again, finds the spectrum is convex. You can add Chern-Simons terms to the theory and at level K, so that's another large parameter. And one finds that Chern-Simons terms only make the spectrum more convex. And so all kind of Chern-Simons deformations of the CFTs will maintain convexity of the spectrum. So in all these things, the monopole spectrum is always convex. And I should give a special thanks to Shai Chester here, who really explained all this story monopoles to us. He's really an excellent guy. Actually,
we are running out of time. Sorry, we are running out of time, so you can finish in a few minutes. Would be great.
In 2 minutes, I'll finish. Sorry, yeah, and then okay. So this is an example of the kind of the common game in the sense of the lowest charge operator not satisfying convexity. You can consider a supersymmetric theory with phi cubed, and then you find that the scalar component of this superfield it has a 3D IR fixed point, and you find that the scalar has charge 2 in the appropriate normalization and dimension 2/3. But the fermion has charge 1 in dimension 7/6, so this will not satisfy it. But of course, if you take Q0 to be 2, then it will be fine because phi is a BPS operator, but phi to the n is not. And let me just briefly mention the case of strong coupling and strong versions of the conjecture. So of course, if I said if you have a completely strongly coupled theory, then the conjecture will always be true because of some order 1 Q0, you'll enter the large charge regime. But you could test a strong version of the conjecture, like Q0 should be the lightest charged operator, or Q0 should be the smallest scalar operator charge. And both these things seem to be true in all the CFTs we tested. Although in flat space, which is qualitatively different, of course, to what we said in supersymmetric theories with multiple U1s, there are proposed counterexamples to these. But at least without supersymmetry within ADS, there's no counterexamples we know of. And at least in the CFTs. So one can consider these strong versions, and then you can test those in completely strongly coupled theories, like O2 model in 3 dimensions. And one can calculate this in the strongly coupled theories, and you find that the spectrum is convex. You can check convexity in all these methodologies. And then just one last comment that it's interesting because this theory, for example, is actually describing superfluid transition in helium very well. And so the dimension of these operators can actually be measured experimentally. And so in that sense, one is making actually connections with theories that can describe systems in nature. Of course, any transition is a CFT. any phase transition is described by some CFT, and if you can make some general statement about the operators in any kind of CFT, then you're making statements about phase transitions in nature. So in this case, these numbers, this convexity, you can really relate to something you can experimentally measure. So I think that's interesting, and it could lead to sort of summarize. So we propose that a natural formulation weak gravity shows in terms of the binding energy of a particle. This leads to a CFT dual statement, which is that the spectrum of charged operators should be convex. Seems to hold in all the examples we tested so far. If we demand unitarity in a stable vacuum, of course, we need to keep testing it in the absence of a proof. There is opportunity for a proof because CFTs are well defined, unlike quantum gravity theories. So if you make a sharp CFT statement, there is a possibility for a proof in that sense. Of course, if you prove the more general convexity statement, then you automatically also prove the weaker statement, which is a kind of formulation of the weak gravity conjecture in ADS. And as I said, if there really is a statement about any CFTs, then those describe also really systems we can create in the lab, like the phase transition of helium. And in that sense, there is a renewed opportunity to making connections with experiments and predictions and tests in that sense. So even if we don't know the CFT describing a phase transition, if the conjecture is correct, then there's still some CFT and there will be convexity, and then you could try to actually potentially measure that. Okay, so to finish with the Oguri-Hertzsprung-Russell diagram, the idea is that reformulation of the weak gravity conjecture can move it away from what we call the main sequence of conjectures in this direction. So first of all, make it useful in the sense of statement about CFTs and possibly even connections with experiments, and also make it more robust because you can try and even prove it using CFT axioms. So make it into a giant conjecture or a super giant conjecture. So I'll finish with this. That's it. Sorry for overrunning a bit. Yeah. Thanks.
Okay, thank you very much for the talk, Eran. So are there further questions? I like the diagram.